Hello everyone, welcome to Multivariate Statistics and Machine Learning. In this video I will briefly sketch how to train the classifiers we learned in the last video to data and show you some examples. If you would like to have a look, then check out sections 4.4 in the lecture notes. Okay, so I mentioned before that supervised learning has a training step and a prediction step. So we have a training step and prediction, and both steps they apply different types of data. So in the training step we have training data, x1, xn, and they are multivariate, and sometimes we have a label here, xtrain, so that we really denote them that these are training data, and we have labels available for all of these data sets. So they're also ytrain. So this is basically a complete data set. And then we have a test data, one or more, and we would like to find a prediction of our label. So that's and we've seen now the so examples of classifiers. So we have the base classifier, and then we had the normal base classifier, and then as special cases we had QDA, LDA, and DDA. And you've seen that they have we have discriminance functions, of course. So dk QDA of x, and similarly we have dk LDA of x. So this was a quadratic function, and this was a linear function, and then of course we also have DDA of x, and of course all of these involved estimates of, or involved sigma, or sigma k for QDA, mu k, and pi. So we have all these parameters, and if we know the parameters, then of course we can predict y, but in practice we have to actually learn the discriminance function from the data. So our task, learn or estimate dk. So we actually have to estimate this function. So we need to get a function like this. So I'll put a head on top. So we have dk x, and this head here, this comes from the training data. So we estimate from X train and Y train. And this here is actually our test data. So we have different functions. So the training data estimates the parameters of the discriminant function, and the actual value they put into this discriminant function is actually the test data. So let's look how many parameters do we actually need to estimate. So for how many parameters do we need to estimate? For QDA, DDA, LDA. So let's look. So what we, for all of them, so for all methods, we need to estimate pi 1 to pi k. So that's what all methods have in common. So for QDA, we need sigma 1, sigma 2, sigma k. So that's a lot of parameters. So that's where a lot of data is needed. For LDA, it looks better. We need only sigma. And for QDA, not QDA, DDA, we actually only need sigma 1 squared and up to sigma d squared. So in short, the number of parameters are as follows. So for QDA, total parameters, total number of parameters. For QDA, it's k for the number of classes, but actually it's k minus 1, it doesn't matter, plus kd plus k times d minus 1 divided by 2. So let's put this here. So k minus 1 plus k times d plus k. So k times d is because we have I forgot, of course we need the means as well. So we need mu 1, mu k for all of those. So that's where this comes from. So we need the mean parameters times dimensions. Then we need k minus 1s is for the pi. And this is the number of parameters. So for LDA, it's k minus 1 plus d, because we only have one kd plus d. So we still have the number of means plus d times d minus 1 divided by 2. So, and if d is large, that's a massive difference. So the difference here is basically that we only estimate one covariance matrix. And then in DDA, we have the largest savings. So we have k minus 1 plus k times d for the means plus d. So that's the parameters needed for diagonal discriminant analysis. So DDA is linear in D, and these are actually quadratic in so because QDA and even LDA is quadratic in D, we need to regularize QDA and LDA. So for high dimensions, we need to regularize QDA and LDA. And in earlier discussion, so when we discussed about estimating the covariance matrix, so recall Bayesian estimation or shrinkage estimation of the covariance matrix sigma, and this is where this comes in now. So for QDA and LDA, we need regularized covariance estimates if D is large, and large typically means that we have, even if the sample size is still larger than D, but often it actually can happen that D is smaller than N. So, and this leads, for example, to a method called SDA, which is basically shrinkage LDA, and in the worksheets you use this method. So there's a R package that implements this, and you use this in the worksheet to analyze some data. Okay, so that's some theory. So let's also look at the estimated decision boundaries. So if we simulate data, or we have some actual data, you can try to fit the first step is to try to fit the discriminant function, and then we can do some investigation how these things look like. And for this, let's check the figure in the lecture note. So what you see here is the following. So in the what I've done here is to simulate data in two scenarios. So here we have 4 groups, and these groups are not nested. So you can see here the 4 colors corresponding to the 4 groups. And then I have trained LDA and I've trained QDA on this data set. So this is estimated, all estimated. And in the second column, you see the decision boundaries provided by LDA. And you can clearly see they're all linear. So the neighboring areas, so as I said, this is estimated. This is not the theoretical one. So this is the estimated from this data by estimating the means and the covariance matrix. So in this case, we have because it's LDA, we have a common covariance. If we don't have a common covariance, you can see that we have like kind of curvy boundaries, not everywhere, but sometimes, and then you get this shape. So whether this is better or this is better, that doesn't when we discuss how to evaluate the results, we leave this up. Basically, depends on the case whether this is actually QDA is better than LDA, but if you look at just the scatter plots, you get the impression that QDA is actually believing that this area here belongs to the orange group, but in reality it's probably not the case. A second case here is when you have nested models. So you have one group and that's one thing inside the other. And the interesting thing is when you simulate this, then, so these are both normal data. When you apply LDA, of course, you don't get anything because there's no linear boundary that can actually represent this. So it all thinks that it's only one group. Whereas when you do QDA, it does find the two groups, at least to some extent. So having more parameters sometimes is a problem because you need to estimate them, but having more parameters often is also helpful because you can actually address the data at hand. So while we need to be careful about our parameter numbers, we also need to be careful about that we don't remove signal from the data by making a model too simplistic. Okay, that's it for this video, and see you in the next one. Bye-bye.